Welcome to CPT112 Relation presented by Group M1. Let's introduce ourselves. My name is Emedus Lim, and this is Aini Yasmin, and this is Kalista Dennis Gumbaris. What are we going to be learning today? First is definition, properties, operation. Second, representations. And third, relational databases and equivalent relations.
Let us start with part 1, which is definitions, properties, and operations. So, what are you hoping to learn today? First, we will learn about relations and functions. Binary relations is defined as a binary relation R from a set A to a set B is a subset. It is said that relations are more general than functions. Example of binary relations. Let A is equal to 0, 1, 2 and B is equal to AB. 0A, 0B, 1A, 2B is a relation from A to B. We can represent relations from set A to set B graphically or using a table. Now, what is binary relations on a set? A binary relation R on a set A is a subset of A cross A or a relation from A to A. Now, let us look on the examples of binary relations on a set. Next, we will learn about the properties of relations. First, we look at the definitions for reflexive relations and irreflexive relations. So, we go for the examples on reflexive relations. There are two examples. Example on irreflexive relations. Next, we look at the definitions for symmetric and anti-symmetric relations. How about asymmetric relations? This is the definition for asymmetric relation. The last properties of relations is transitive relations. We look at the definition of transitive relations. Lastly, we will learn about combining relations. Given two relations R1 and R2, we can combine them using basic set operations to form new relations. Example on combining relations. Let A is equal to 1, 2, 3 and B is equal to 1, 2, 3, 4. The relations for R1 and R2 are given where it can combine using basic set operations to form new relations. This is the answer from the previous question. Composition is defined by R1 is a relation from set A to set B and R2 is a relation from B to set C. Then the composition of R2 with R1 is a relation from A to C. Power of a relation is defined as follows. Let R be a binary relation on A. Then the powers R to the power of n of the relation R can define by basic step and inductive step. The powers of a transitive relation are subsets of the relation. This is established by the following theorem as presented. Now, let us recap on what we learned in part 1. First, we learned about the function as relation and relations on a set. Second, we learned 6 properties of relations. And lastly, we also learned about composite and powers. So, that's all for part 1 in this chapter.
Hi everyone, welcome to part 2, which is representation from group M1. In this part, we will learn about 0-1 matrices, Boolean operations, and the graph, or we call it as directed graph. Firstly, what is 0-1 matrices? 0-1 matrices is a matrix that contains entries are either 0 or 1. Algorithm operating on discrete structure are defined by the following Boolean operations. Now let's look at the example. First, we find the matrix representing R, which is R equals to 2, 1, 3, 1, 3, 2. Then we get the 0-1 matrices for R is 0, 0, 1, 0, 1, 1. Now we will look at the Boolean operations. Boolean operators are the word and, or, and not. Boolean operation have two types, which are Boolean or join we use for union of two relations, and Boolean and or meet we use for intersection of two relations. Let's discuss more on join and meet. For join, A join B equals to 1 if A or B is equals to 1. But for meet, A meet B equals to 1 if A and B is equals to 1. But if one of them is 0, then A meet B is equals to 0. Now we will look at the example using Boolean operations. Relation R and S represented by the following matrices. For question A, we use Boolean OR to get matrix R join matrix S, while for question B, we use Boolean AND to get matrix R meet matrix S. For the composite of two relations, relation A and B, we denote it as MA and MB. Composite of BA is the Boolean product of MA and MB. Power of relation, we denote it as R to the power of n. We use the given formula to get matrix R to the power of n. Now let's look at the example. Question asked to find matrix representing R square, where MR equals to 1, 0, 0, 1, 0, 0, 0, 1, 0. Then we solve the question by substituting MR and n equals to 2 into the formula to get the answer. Now let's move to the graph parts. Here is some definition and requirement for the graph. We should know the vertices and the edges. An edge from AA, we call it as a loop. We use arrows to display the graph. We will learn how to make a digraph. Let V be the set of 1, 2, 3, 4, 5, and 6. We display the graph by referring to the set E by using arrow. We start from 1 to 2, then followed by 1 to 4 until 6 to 3. Then we will get this digraph. 3, we call it as a loop.
Part 3. Relational database equivalence relations. What is an array relation? An array relation is a subset of the sets A1 cross A2 cross A3 cross until AN. And the domains are A1, A2, A3 until AN. The degree will be n. For example, let R be A, B, C, the three tuples where A divides B and B equals to 3C with A, B, C in the integer set Z. What is the degree of R? What are the domains of R? Is 2, 15, 5 in R and is 3, 9, 3 in R? Well, the answer is 3 for the degree because Z cross Z cross Z. Second will be integers, integers, integers. And 2, 15, 5 is not in R because 2 cannot divide 15. And 3, 9, 3 is in R because 3 divides 9 and 9 equals 3 times 3. Relational database consists of n tuples called records. An entry is a single piece of data in a database. A field is a grouping or category of similar information, entries to the n tuples. A record is a complete description of all the fields related to one item in a table. This is what we have learned so far. As a summary, a table consists of entries, row, and columns, where rows are the record, columns are the field, and every cell will be the entries. Everything makes up to be the table. This is what we learn. Alright, now, what is primary key? Primary key is a domain of an n-array relation whose value uniquely determine the n-tuples, and uniquely means no two records can have the same value from the same primary key. Which of the following fields are primary key? Student name or ID number? Well, the answer is ID number because it's unique to everyone. Student name might be the same. What are composite keys? It's a Cartesian product of a set of domains of the combination of which uniquely identifies n tuples in an array relation. Name cannot uniquely identify because there are two aria, but when you combine them with city, it can uniquely define the n tuples, so they are the composite keys. Operation on n array relation with projections maps the n tuple to m tuple, and we have joined combine two tables into one if they share the same field. Find projection 1, 3. Well, the answer is Ali and Bang A because it's very obvious. You just need to find the first and the third one. Now, example, find join A and B. A and B share the same name field. So, when you combine them together, instead of 4 columns, there will be 3 columns. And this is the answer. Now, equivalence relations. A relation on the set A is equivalent if it's reflexive, symmetric, and transitive. For example, let a relation R be on self all real numbers defined by x, r, y if and only if x minus 1 is an integer. Is R an equivalence relation? Where the solution is R is reflexive because x minus x is 0 is an integer, so x r x. R is symmetric because if x r y, then y r x is also integer. R is transitive because x r y, then y r z, therefore implies x r z. Hence, R is an equivalence relation. Equivalence classes. Let R be an equivalent relation on the set A. The set of all elements that are related to an element A in A is called equivalent class. Now let's see equivalent classes. Notation bracket A subscript R, and if B is an element of this class, then B is a representative of that class. For example, so what is the equivalent class of the word math, and give an example of representation? The solution is math is the set of all English words containing 4 letters and exam is a representative. Partition. The definition is a partition of a set as a collection of the disjoint non-empty subset of S that have S as their unit, and this is the theorem. Now, for the derived definition of partition, remember it's a collection of non-empty subset of S, and every element of S is in exactly one element of the partition P. Are the following partitions of S? Well, first is yes, second is no because there's an empty set, third is no because there's element 6, and 4 is no because 4 appeared 2 times, and fifth, 5 is not in the element. Therefore, thank you very much for this presentation.